Hey guys, Mrs. Stans here. So we're on lesson 5 in our exponential unit. You can see that today we will be comparing and contrasting linear and exponential functions. You should be able to do the do now on your own, but of course I'm going to do it in this video. And then we will do the development together, and then if there's time you can do your homework. A function passes through the points 0, 5, and 110. Katie and Adam are in a heated debate over who wrote the correct function. So who is correct? So I can tell just from looking at this that Katie wrote an exponential function while Adam wrote a linear function. So if it's an exponential function, this number here should be the y-intercept. 0, 5. That is a point on the y-axis. So sure, the y-intercept is at 5. And then she says that the multiplying factor is 2. So if I look at the outputs from 5 to 10, it is multiplied by 2. So I agree that Katie's function would fit these 2 points if it's exponential. So let's see about Adam's. Adam says that the slope of the function is 5. So if we use the slope formula, 10 minus 5 over 1 minus 0, we get 5 over 1, which is 5. So I agree that the slope is 5, and we already said that the y-intercept was 5. So guess what? Adam's function is correct also if it's a linear equation. So that's what the problem is. If we only have 2 points, it's not enough information to decide whether it's linear or exponential. If I have 2 points, I'm just going to put 2 random points, pretend these are them, I can draw a straight line through it. But if I have the same 2 points, I can draw something that looks exponential through it. So 2 points just isn't enough. They shouldn't be debating. Not enough information was given. So let's look at what we know about exponential and linear functions so that we can always determine which is what. So we can tell if something is linear by the look of the graph. What is it that we see in this graph? Well, we see that it's a straight line. What we can see is a constant rate of change, right? I could draw a staircase on here where all the steps are the same. So I'm going to say constant rate of change. I'm using ROC for rate of change. But when we look at this exponential graph, it's not straight. So it can't be linear. But how do we know it's exponential and not like quadratic? Remember, quadratics are curved also. They're those U-like shapes. Well, a quadratic equation will decrease and increase, has a turning point. Exponential equations don't have turning points. They're always constantly increasing or constantly decreasing. Now, next, let's look at the table of values. So in order to have a constant rate of change, there must be a constant number that we actually keep on adding on. Like the rate of change of this table is plus 3 over 1, 3 over 1. Because remember that slope, I shouldn't write it here. How about here? Slope is equal to the change in y over change in x, right? It's y2 minus y1 over x2 minus x1. So we should look at both how the y is changing and how the x is changing. And if it's constant, then it's linear. So this rate of change is constantly 3 over 1. This doesn't have a constant rate of change, right? This is going up 0.25 over 1, then it's going up 0.5 over 1, then it's going up 1 over 1, up 2 over 1. It doesn't have a constant rate of change, but it does have something else. It has a multiplying factor. And the multiplying factor in this case is 2. So if you can find a multiplying factor, it makes it exponential. If you can find a constant rate of change, constant, then it's linear. If we look at the equation, linear equations are always in the form of y equals mx plus b. The exponent of the x is a 1 here. If you look at exponential equations, the x is the exponent, right? So that's a big difference. In linear functions, m stands for slope, which is actually the constant rate of change, and b stands for the y-intercept. Actually, it is a y-intercept, but it does show us even like shifts. It tells us whether the function shifts up or down along the y-axis. And then the exponential function, remember, a is your y-intercept. It does not represent a shift. And b is your multiplying factor. Or we can call it our growth or decay factor. I have to tell you that we can shift with exponential functions, but there would be something else here. Like I'd have some other number added on at the end. I'll put a plus c. That c would be our shifts up or down. So when something's added on at the end, like this was added on at the end, this was added on at the end, that represents shifts up or down. Keywords for both linear and exponential, there's not very many they'd use for linear. Really, we're looking for a constant rate of change. So if something is constantly changing the same way over time, it's linear. But there's actually quite a few things that make us think about exponential functions. We usually see percentages. We can see words like double or triple or twice. Maybe not twice. Let's say double, triple, half. What else? Like compound percentages, like when you put it in the bank, your interest compounds. Of course, decay and growth. Right, so these are all words that make us think about exponential. So, name the type of function represented in each graph below. Well, since this is straight, it's linear. Since this is curved and constantly increasing, it's exponential. And since it's constantly increasing, it's actually exponential growth. While this one is constantly decreasing, so it's exponential decay. And now it's time to look at some tables. So we have to determine whether it's exponential or linear, and then we have to write the equation. So in this table, I'm first going to see if I can add the same number again and again, because that would say that there's a constant rate of change, or if I can multiply by the same number again and again and again, because then that would be a multiplying factor. So I notice quickly right here, I can multiply by the same number. I can multiply by 2 each time. So it must be exponential. And it's exponential because it has a multiplying factor of 2. And then if I were to write the equation for this function, I first look for the y-intercept. Remember, y-intercept always has an x-coordinate of 0. So the y-intercept is 5. The multiplying factor is 2 and gets raised to the x power. Remember, if ever you think you're wrong, you could, or if you're unsure, you plug this into your calculator and make sure it generates the same table. Part B, we look and see what's happening here. And there actually is a constant rate of change. I can add 3 each time while this goes up 1 each time. It's important to recognize the change in y and the change in x, just in case it's not changing the same. So this is linear because there's a constant rate of change of 3 over 1. So if I write the equation in y equals mx plus b form, the slope is 3, and the y-intercept is right here, right where the x coordinate is 0. Okay, C. Well, I can see it's decreasing. Just because it's decreasing doesn't tell me what kind of function it is, though. Remember, linear equations can decrease, exponential equations can decrease. We just have to see if it's decreasing at a constant rate of change or not. This is going down 20, while this is going up, down 2, sorry, well, that's going up 1. And this is going down 2, while this is going up 1. And down 2, while going up 1. Guess what? There's a constant rate of change. It's linear because the constant rate of change is negative 2 over 1, which means I can write y equals negative 2x. Don't forget to look for your y-intercept plus 16. B. So this one is also decreasing, but it's not decreasing at a constant rate. To me, it looks like it's dividing by 3. But when we talk about exponential functions, we don't like to talk about dividing by a number, even though that might be the first thing you notice. If I'm dividing by 3, it actually means that I'm multiplying by 1/3. So it's exponential because the multiplying factor is 1/3. So the equation, right here's my y-intercept, is 18 times 1/3 to the x power. So something that I just want to point out before I move on right now, since C was constantly decreasing and D was constantly decreasing, but they were two different types of functions, I want to point out that in order to have a decreasing linear function, the rate of change must be negative. In order to have a decreasing exponential function, the multiplying factor must be between 0 and 1. It won't be negative, right? So just like keep those things straight. All right, so consider the 2 points 0, 6 and 1, 3. Create a linear equation that passes through these points in y equals mx plus b form, and an exponential equation in y equals a times b to the x form that also passes through these points. Yeah, because this brings us back to the do now, that if you only have 2 points, I could draw a straight line or I could draw a curve. So 0, 6 is right here. 1, 3 is right here. So I could draw a straight line going downward or a curve going downward. Before I draw it, I want the equation so I could plot some more points and be more specific. So if I do my linear one first, using the points 0, 6 and 1, 3, I want to find my rate of change. 3 minus 6 over 1 minus 0 is negative 3 over 1. the rate of change is -3. So y equals -3x. I just need my y-intercept, which actually is given to me, 0, 6. So there I go. So if I graph this, I'm constantly going down 3 over 1. So I'm going to put some more points. Linear equations will go to positive infinity and negative infinity for the domain and for the range. Oops. It's hard to draw a straight line with my pen that I use here. So this is y equals -3x plus 6. They didn't ask us, but I'm going to talk about it. The domain for this is all real numbers. It goes out forever to the right and left. The range for this is also all real numbers. Goes forever down and forever up. But now when I do my exponential function, I need the multiplying factor. So you look at the y values, the outputs. Looks like divide by 2, which means I'm actually multiplying by a half. So the multiplying factor is a half, and the y-intercept is 6. So y equals 6 times 1/2 to the x power. I want some maybe points to look at. So if I put in here 6 times 1/2 to the x power, and look at my table, I could first of all make sure those 2 points are there to verify that I wrote the correct equation. So here's 0, 6, and 1, 3. So I did pretty good. And I should plot as many points as I can. It gets difficult with exponential functions. So that's all I'm going to write down. I can't even fit the -112. It's off the graph, like up here. 0, 6. Let me just change this color for a second. 1, 3. All right. Now remember, this gets closer and closer, but never hits 0, because there isn't any half to any power that equals 0. Whenever you draw a linear and an exponential function on the same graph, right in this area here, it's never going to be one on top of the other, because an exponential function is curved while a linear function is straight. So there's always, like, you could always see a little bit of difference in it. It's hard to do it by hand, especially on a computer like this. It doesn't always come out as neat as you want it, but you do the best you can. Like, this would give me full credit. And I think I answered all the parts to that. So example 3. Oh, you know what I didn't do? I didn't label this. Y equals 6 times 1/2 to the x power. Oh, the other thing I didn't do, I wanted to talk about domain and range. So the domain of this exponential function is all real numbers. It goes forever out to the left and the right. The range won't ever be all real numbers though, because remember, an exponential function starts to flatten out someplace and approaches a horizontal line and never touches it. So far we've been dealing with exponential functions that are approaching the x-axis, but honestly it can shift. It could approach some other horizontal line. But that horizontal line it approaches, it never touches, so it's never going to touch 0. And this one is going forever upward, right? So the range will always have some number that it's approaching, never like negative infinity to positive infinity. Example 3, the function t of x is shown in a table below. Determine whether t of x is linear or exponential and explain your answer. So right here, this is going down by 2.5, while this is going up 2. Down 2.5, and still this is going up 2. Down 2.5, up 2, and down 2.5, and up 2. So it does have a constant rate of change. So since there is a constant rate of change equal to negative 2.5 over 2. That's important. The rate of change is just not negative 2.5. It's negative 2.5 over 2. Negative 2.5 divided by 2 is negative 1.25. So the rate of change is negative 1.25. Since there is a constant rate of change equal to that, this is a linear function. This sentence answers the question exactly. It says determine whether it's linear or exponential. I did. And it says explain your answer. And by me starting off here with saying since there's a constant rate of change, that's my explanation. And finally, the function f of x is shown in the table below. Determine whether f of x is linear or exponential. Explain your answer. You could see there's a multiplying factor. Right? We have to be careful what a multiplying factor is, though. This people mess up all of the time if we wanted to write the function. It just says determine if it's exponential or linear. It doesn't tell us to write the function, but I just want to point this out. So it looks like we're multiplying by 4, right? It feels like I might want to say the multiplying factor is 4. It's actually not, because look it's not multiplying by 4 for each one x. This is going up by 2. So this is kind of like a trick. Not crazy about tricks. The multiplying factor is not 4. The multiplying factor is actually 2. Let me just change my color for a second. Because if they actually put the 0 in here and the 2 and the 4 and the 6, I would have to multiply by 2 to get a 1, multiply by 2 to get the 2, multiply by 2 to get a 4, multiply by 2 to get the 8. You see they're like tricking us? So it's exponential because there is a multiplying factor of 2. So many people would want to say it's 4. If I wanted to write this function, it would be 1 times 2 to the x power. Right here's my y-intercept. And you can test it on your calculator even if like you're not certain if you did it right. But I did do it right. So that's this lesson. And you have your homework 3 pages worth. It doesn't take so long though, and I will see you soon. See you, bye.